Since the dawn of humanity, humans wondered about shiny objects in the sky, and they realized that some of them are stationary, some of them have circular orbits, and some of them show up once and never again, and others have a very complex trajectories. Today, we will investigate together the physical laws that explains all this different and complex motion. Welcome to Infinite Synthetica, and this is planetary motion. Before we begin, I must note that there is 3 prerequisites to this video: calculus, Cartesian and polar coordinates, and vectors. Don't worry if you don't master all these prerequisites. I will be suggesting throughout the video resources that will help you get comfortable working with them. In order to talk about position, we need to specify every point in the space around us, to give every point in our 3D space a specific code. And there is a lot of ways to do that, and Cartesian coordinates is just one of them. So let's see how Cartesian coordinates manage to do that. Let's choose a point as our center and let's call it O, and 3 perpendicular lines, and let's give each one of them an orientation by specifying a unit vector. Now let's imagine a position. This position can be represented by a vector which tail is in the origin, our coordinate system, and the tip is on that position. You can see that V is very specific to that position. No other point in the 3D space can have the same vector V. It's like having a code that specifically identifies that position. In our coordinate system, the vector V is represented by 3 distinct numbers, which represents how much of each of the unit vectors we need to add up to get the vector V. So V can be represented by a 3D tuple containing Vx, Vy, and Vz, or Vx times the vector I plus Vy times the vector g plus Vz times the vector k. Note that throughout the video, I will be representing vectors by a letter and an arrow over it, or a hat. The hat just means that the length of the vector is 1. Polar coordinates is just like Cartesian coordinates. It's just a way to specify points or positions in space around us. The only difference is Cartesian coordinates could be used in 2D space or 3D space, but polar coordinates is specifically designed for 2D space. Let's choose a center and let's call r the distance between the center and the point or the position that we want to encode in our coordinate system. And let's choose a reference for our angles. Let's choose 2 other unit vectors, er and e theta. Er is just direction from the center to the position that we want to encode, and e theta is the direction of positive angles. Now, that position could be encoded as a vector v, which equals to r times er, or as the 2D tuple r theta. The power of polar coordinates is in contrast to the Cartesian coordinates. It's a very dynamic system, meaning that imagine if the position moves through space. Er will always point from O to that position, which will be very handy later on. Let's shift our attention to a very important question, which is, what is the relation between the polar coordinates and the Cartesian coordinates? To answer that is just a matter of applying Pythagoras' law. So it turns out that er is equal to cosine theta I plus sine theta g, and e theta equals minus sine theta I plus cosine theta g, and I cannot emphasize the importance of these 2 equations. Johannes Kepler, and I'm sorry if I butchered the name, he lived from 1571 to 1630, and this man managed to do something very fabulous. Just from the analysis of enormous amounts of data about planetary motion, he manages to come up with 3 laws that encapsulates all the complexities of planetary motion, called Kepler's laws. First one asserting that planets have elliptical trajectories and the sun is in one of the focus points of ellipse. Second is swept areas in different times but within the same intervals is constant. The third is the period squared is proportional to the semi-major axis cube. Now, mathematically speaking, the first law is the equation of an ellipse, which is r theta equal p over 1 plus minus e cosine theta. The plus or minus here depends on our choice of the focus point and the angle 0, because if we choose the left focus point, clearly the biggest r correspond to theta 0. So, for r0 to be maximum, the right hand side should be p over 1 minus e. So the full equation would be r theta equal p over 1 minus e cosine theta. With the same reasoning, if we choose the right focus point to be our origin, we just flip the sign. To explain the second law, imagine an object moving on the elliptical trajectory. The area swept by that object in equal intervals of time is equal. In other words, time derivative of the area is constant. It turns out to be that dA over dt equals h over 2. H is just specific angular momentum, which is a constant in our case, and the area swept is equal to h over 2 times time interval. The third law states that period squared equal to 4 pi squared over gm times a cubed. T is the time that the object takes to return to its initial position. G is the gravitational constant. A is the semi-major axis of the elliptical trajectory. And m is the mass. Not the mass of the moving object, but the mass of the object that creates the gravitational field. In our case, is the sun. It's located in one of the focus points. Kepler's laws are powerful, but the problem is that they do not sit on a physical basis. So, in the pursuit of finding a physical basis for Kepler's laws to sit on, we will shift our attention to Newton's laws. Isaac Newton, the last magician, lived between 1642 and 1726. He gave us the total of 4 laws that are absolutely powerful. And giving a physical basis to Kepler's laws is just a byproduct of their strength. Newton's laws consist of 3 laws of motion and 1 of gravity. The first law of motion: objects stay in linear uniform motion or at rest unless a force acts on them. The second law states that the net force equals mass times acceleration. Third, every action, which is a force, has an equal and opposite reaction, which is also a force. The law of gravity, or the universal law of gravitation, asserts that every mass in the universe attracts every other mass with a force reversely proportional to the distance squared and proportional to the mass. Mathematically speaking, the first law of motion is just mass times acceleration equals 0. The second, the net force equals mass times acceleration. Third, the force exerted by an object A on an object B equals minus the force exerted by the object B on the object A. The law of gravity states that the force of gravity equals minus g times m over r squared times the unit vector er. Enough theory already. Imagine a massive object like the sun, and imagine another object lighter and circulating the first object like Earth. Assuming that the trajectory of the Earth is circular, we can use Newton's laws to derive the velocity of the Earth. Notice that we know in circular motion that the acceleration is equal to the velocity squared over r. We will also assume that the force of gravity exerted by the Earth on the sun is insignificant because the sun is very massive. In the end, we get that the speed of the Earth equals the square root of g times m over r. I want you to wonder on a question. Imagine that the Earth is stopped. We know that if we give it a speed equals to the square root of gm over r, that the Earth will be in a normal circular orbit around the Sun. But what if we give it a lesser speed or a higher speed? And how much speed we need to give to the Earth in such a way that the Sun can never pull it back? We call that escape velocity. Now we will try to calculate it. The way to tackle this problem is by considering how much energy we need to give to the Earth to reach infinity against the pole of the Sun. You could say, why infinity? Because if we choose any finite distance from the Sun, theoretically the Sun can pull the Earth again given enough time. And we want to give Earth just enough energy to reach to infinity. So when the Earth gets to infinity, its total energy will be zero. In general, the total energy of the Earth is the kinetic energy plus the potential energy. The kinetic energy is 1 over 2 mv squared, and for a conservative force like gravity, the potential energy is just the integral of the force of gravity with respect to distance. After simplifications, we get that the total energy of the Earth is just 1 over 2 mv squared minus gmm over r. Notice that the gravitational potential energy is always there. The question is how much kinetic energy we need to give to the Earth in such a way that it counters the gravitational potential energy, meaning how much speed the Earth needs to be exactly zero at infinity. Solving for v, we get the escape velocity, which equals to the square root of 2 times the gravitational constant times the mass of the Sun over the distance r. Notice that the escape velocity is bigger than the circular velocity by a factor of square root of 2. Now, the question that poses itself is the following. So, we know that if the Earth have the velocity of vc, a circular trajectory, and if we give it a speed of ve, it will escape the gravity of the Sun. So basically it will go and never come back. What if we give it a speed bigger than ve, or a speed that's between ve and vc, or a speed lower than vc? What will happen then? I hope this drawing clarifies every possible case. Now that we have a better understanding for Newton's laws, the rest of this video will be dedicated to deriving Kepler's laws from Newton's. We will be using polar coordinates to do that, and I want to shed the light on something. In Cartesian coordinates, velocity and acceleration are the first and second derivatives of the position function, respectively. In polar coordinates, the formulas for velocity and acceleration are not that trivial. So, our first step is to derive the velocity and acceleration formulas in polar coordinates. Recall that ER equals cosine theta I plus sine theta g, and E theta equals minus sine theta I plus cosine theta g. Also, notice that the derivative of ER with respect to theta is just equal to E theta, and the derivative of the vector E theta with respect to theta is equals to minus ER. This result will be excessively used in the next steps. Velocity is the time derivative of a given position function, just like Cartesian coordinates. The difference is only on the way we represent the position vector. In polar coordinates, the position vector is just r, er, and r is a function of time. And we get the formula for velocity in polar coordinates, which is the time derivative of r times er plus r times the time derivative of theta times e theta. Notice the use of the chain rule in the second step. To get the formula for the acceleration, we just need to differentiate the velocity with respect to time. After a straightforward application of differentiation rules, we get that the acceleration is equal to the second time derivative of r minus r times the time derivative of theta squared er plus r times the second time derivative of theta plus 2 times the time derivative of r times time derivative of theta times e theta. This is a recap for position, velocity, and acceleration formulas in polar coordinates. Now we have all we need to derive the first Kepler's law. Notice the definition of the angular momentum, which is the cross product between position vector r and the velocity v, scaled by the mass m. After we substitute v for its formula and the cross product of a vector with itself is 0, we get the final formula for the angular momentum magnitude, which equals the mass times r squared times the time derivative of theta. Now we will introduce the specific angular momentum h, which is just the angular momentum over m. Now for the actual derivation of the first Kepler's law. We will invoke the second law of Newton's laws, and the net forces exerted on Earth is just the force of gravity exerted by the Sun. After that, we substitute the acceleration for its formula in polar coordinates, and we get the following two equations by making sure that the expressions corresponding to the ER vector are equals and the two expressions corresponding to E theta are equals in the two formulas of acceleration. Notice that the second equation is closely related to the time derivative of the specific angular momentum. So we get that the derivative of the specific angular momentum is 0, which implies that h is a constant, which is a very important result. A following reasonable step is simplifying the first equation by using the formula for h. So we get the second time derivative of r minus h squared over r cubed equals minus g times the mass m over r squared. So to get the trajectory, we just need to solve for r. Before we attempting to solve this differential equation, we will try to simplify it further by using a change of variable. So u equals 1 over r. Keep in mind that we want to solve r as a function of theta. For that, we are interested in the relationship between time derivative and the second time derivative r with the theta derivative and the second theta derivative of u. Achieving that is a straightforward application of the differentiation rules and the fact that h is a constant. After substitutions, we get a second order differential equation in the form of second theta derivative of u plus u equals g times m over h squared, which has a general solution in the form of u equals g times m over h squared times 1 minus e cosine theta. E is a constant called eccentricity. Switching back to the variable r, we finally arrived at the first Kepler's law, which is r of theta equals h squared over g times m times 1 minus e cosine theta. Now let's derive Kepler's second law. So the idea is to approximate area swept by the sum of an infinitely small triangles defined by r and d theta. Actually, they are not triangles because r d theta is an arc, but when the triangles are very small, we can safely assume that they are triangles. So each triangle has an area of r squared d theta over 2. And by taking the integral between two angles, we get swept area. So the area A equals 1 over 2, the integral between theta 1 and theta 2, r squared d theta. And we can invoke the chain rule to change the variable that we integrating with respect to, from theta to time. So we get that the area A equals 1 over 2 the integral between t1 and t2 r squared, the derivative of theta with respect to time dt. Notice that we can substitute h, and finally we get the expression for the area A, which is h over 2 factor of t2 minus t1. From this expression for the area, we can actually infer the second law of Kepler. If the interval t2 minus t1 is equal, so does the area. And just for fun, let's calculate the derivative of the area over time. We expected it to be a constant. Let's see. So we get that the derivative of the area with respect to time equals h over 2. And by that, we complete the derivation of the second law. Now, for the derivation of the third law, the following drawing illustrates the semi-major axis and the semi-minor axis of an ellipse, which are represented by A and B. Rmin and Rmax are respectively the minimum and the maximum distance from a focus point. For the derivation, we need a lot of properties of an ellipse, but I will assume that you know none of them, so we will derive them also one by one. The first one is obvious. A equals Rmax plus Rmin over 2. Notice that Rmax is just R of 0, which equals to h squared over gm factor of 1 minus e. And in the same way, Rmin is equal to R of b, which equals to h squared over gm factor of 1 plus e. We add them up and simplify, and we get that A is equal to h squared over gm factor of 1 minus e squared. We have that the area of the ellipse is equal to pi times AB, and we get previously that the area of an ellipse is h over 2 times t, which is the period. So we get pi AB equals h over 2 times t, and by that we get our first link between A and t. Notice that given a point in the ellipse, the sum of distances between the point and the focus points is equal to 2a. We will take advantage of this property, and by defining the distance between the center of the ellipse and the focus point as c, and by that we get our third property, which is a squared equals b squared plus c squared. After simple algebraic manipulations, we get Rmax equals a plus c and Rmin equals a minus c. And by taking Rmax minus Rmin, and finally we get c equals a times e. Now we have all the properties that we want. So let's go for the actual derivation. In straightforward steps, we get b equals a times the square root of 1 minus e squared. And now we substitute b by its formula in the equation we get from the area. Also, we have an expression that links between h and a, so we're gonna substitute h by its expression, and by that we get b times a squared times the square root of 1 minus e squared equals the square root of g times m times e factors of 1 minus e squared times t over 2. Notice that we can simplify the square root of 1 minus e squared from both sides, and by squaring both sides and by a simple rearrangement we get t squared equals 4 pi squared over g times m times e cubed, and by that we finish the derivation of the third law. So we managed to put Kepler's law on a physical foundation thanks to Newton's laws, and by that we finish our video. Thank you for watching.